of Lab 2 charge tapes revisited. As an introduction, some key ideas are Coulomb's law, which calculates the force between two charged particles at rest. We can see the equation here at the bottom. The electric field of a distributed charge, which is simply a summation of all the individual electric fields produced by different point charges. We can see the equation up here. Newton's second law, which we're using the kind of momentum aspect of it, delta P over delta T. We talked about this in Lab 1. A body at rest stays at rest till a force acts on it. Same for constant velocities. Another formula we'll find helpful is the equation for gravity, just being mg. As an objective, we wanted to further investigate our results from Lab 1 by creating a more advanced, more in-depth model for calculating the electric force and charge on our tape. And then we wanted to use this new program to model the tape as lines of charge instead of point charges like we did in the other one. So a preview of our results. The pieces of charge tape obviously showed the same general behaviors we've seen in Lab 1. They met in equilibrium, all of that, but the charge on each piece was found to be about 2.5 e to the negative 8 coulombs in Lab 2, whereas in Lab 1 it was about half of that value, which we'll talk about a little bit later. Some models and assumptions. First, we'll start with assumptions. We assumed that air resistance was negligible. We treated each piece of tape as a line charge as opposed to a point charge, or like a distribution across the entire surface. And then we assumed each U-tape had the same amount of charge, and that charge was evenly distributed across it. So, and then here's a free body diagram that sums up the equilibrium that the top piece of U-tape is facing. So for the experiment, the system were the two charged U-tapes seen down here. The surroundings was everything else, the base tape, everything in the room. Our initial conditions were that the two pieces of U-tape with equal approximate lengths and neutral charges, as well as two pieces of base tape, and then our initial electric charge obviously was 0. So for our experiment, the Lab 1 results you can see at the top here. The length of the U-tape, the mass that we found, the width of it, and then the distance where they met at equilibrium. And then as some of our observations, we found that the magnitude of the electric force on the tape was 2.12 e to the negative 3 newtons, and the magnitude of the charge on the tape was 1.07 e to the negative 8 coulombs. So for our computational model, we declared our constants k and g. Here are our results from Lab 1, and then we made a function to calculate the E field, simply using that equation we went over at the beginning. And then we made a function to calculate the line charge, given the top tape and bottom tape, which we made down here. Then we set our scale there at the bottom. And then we made the actual model itself with all the arrows and everything that we'll see in the next slide. Here you can see it on the right, and the main conclusions and results from this lab are that the force due to gravity and electric force, the magnitudes were about 2.12 e to the negative 3 newtons, and our Lab 2 charge on each tape was 2.5 e to the negative 8 coulombs, which you can see our Lab 1 charge here in the middle. So as an overview and possible errors from our results, so while the new model is still not perfect, it did provide a lot more accurate estimate of real-world conditions by dividing the tape into line segments of charge rather than just a single point charge in the middle. Some errors, though, is that the pieces of tape likely did not have perfectly equal charges. We could have mishandled the tape, causing it to neutralize slightly, and then other surrounding forces were not taken into account, like air resistance and those type of confounding variables. But for our conclusion, what does it mean? So what if you had modeled each of our tapes as a single point charge like we did in the previous lab, compare the estimated values of the charge. So in the first lab, we got 1.07 e to the negative 8 coulombs, and for this lab, when we estimated as a line charge, we got 2.5 e to the negative 8 coulombs. So over 2 times as charged as it was in the previous lab with this new model. And why do these estimates differ? They differ because our first lab was a very, very oversimplification of what the charge actually looks like on a piece of tape. It's obviously not centered in one singular point in the middle of the tape. It's spread across the whole surface. And a line is a better approximation of that than a point is. But even a better approximation would be a whole bunch of line charges summed up across the entire width of the surface. Maybe that's for another lab, but that would be even more accurate. But we're getting closer to what the actual distribution of charge on the tape looks like, so our results are getting more accurate. Thanks.